There's a sound that has followed humanity since the very beginning. A sound older than cities, older than kingdoms, older even than the written word itself. It's the whisper of the ocean, a gentle, persistent rhythm that rises and falls with a patience beyond human measure. If you've ever stood at the edge of the sea, feeling the cool water lap at your feet, you've felt it. The pull, the retreat, the endless dance between land and water that seems, at first glance, to have no reason at all. For thousands upon thousands of years, people have watched the tides. They've watched the water creep up sandy shores in the morning, only to withdraw by evening, leaving behind treasures and mysteries in tidal pools. They've watched harbors fill and empty, boats rise and settle, coastlines transform twice a day as if the earth itself were breathing. And through all those centuries, one question echoed across every shore, in every language, whispered by every generation. Asterisk, what moves the sea? Asterisk, the ancients had their answers, of course. Some said it was the breath of gods, exhaling across the world's waters. Others believed sea monsters stirred the depths, their massive bodies displacing oceans with every movement. There were tales of cosmic rivers, of celestial wheels turning in the heavens, of the Earth's heart beating in rhythm with forces beyond comprehension. Each culture wove its own story, trying to make sense of this beautiful, mysterious phenomenon that governed their lives, their food, their travels, and sometimes their survival. But beneath all those myths and legends, beneath the poetry and the fear, there was something real, something profound, something that connected the smallest tide pool to the furthest reaches of space, linking the moon above to the water below in an invisible embrace that has shaped our planet for billions of years. Tonight, we're going to explore that connection. We're going to trace the hidden science of the tides, from the earliest human observers who first noticed patterns in the chaos, to the great minds who finally understood gravity's invisible hand, to the delicate ecosystems that depend on this ancient rhythm for their very existence. We'll travel to shores where tides rise higher than buildings, and to others where the change is barely whisper. We'll discover how the same force that keeps the moon in orbit also determines when a crab can safely scavenge, when coral can spawn, and how entire civilizations learn to read the language of the sea.so. Settle in. Let the sound of the waves carry you. Because this story, this hidden science, is as soothing as it is spectacular. And by the time we reach its end, you'll understand that the tides aren't just a movement of water. They're a conversation between worlds, a testament to forces that bind the universe together, and a rhythm that has shaped life on Earth in ways we're only beginning to fully appreciate. The ocean is whispering. Let's listen to what it has to say. Long before telescopes or satellites, before the mathematics of gravity or the laws of motion, there were observers. Patient, careful observers who lived their lives by the water's edge and who understood, perhaps better than we do today, that survival meant paying attention. These were the first scientists of the tides, though they would never have called themselves that. They were fishermen, navigators, coastal dwellers, and island peoples whose very existence depended on understanding when the sea would give and when it would take away. The Polynesians were among the greatest of these observers. Across the vast Pacific, from Hawaii to New Zealand, from Easter Island to the scattered atolls of Micronesia, these master navigators developed an intimate knowledge of ocean behavior that still amazes modern scientists. They noticed, generation after generation, that the tides followed the moon. When the moon was full and bright, hanging like a silver coin in the night sky, the tides were stronger, more dramatic. When the moon was new, a dark absence against the stars, the tides were still present but gentler, less extreme. They carved this knowledge into their navigation charts, intricate patterns of shells and sticks that mapped not just islands but also currents, swells, and tidal behaviors. But they weren't alone in noticing the lunar connection. Halfway around the world, ancient Greek philosophers stood on Mediterranean shores, watching the subtle tides of their relatively calm sea and wondering about causes. Aristotle himself pondered the tides, though the Mediterranean's gentle nature made patterns harder to discern than in the dramatic coasts of the Atlantic or Pacific. Still, the Greeks knew there was a relationship. They observed, they theorized, they passed down their questions to future generations. planting seeds of scientific inquiry that would take centuries to fully bloom in medieval Europe. Monks kept meticulous tide tables, recording the daily rise and fall with religious dedication. Their monasteries, often built near coasts or along tidal rivers, required this knowledge for practical purposes: fishing, transport, access to resources. But these records became something more: data points spanning decades, sometimes centuries, that revealed patterns within patterns. The monks noticed that tides didn't just follow the moon's monthly cycle, but also varied throughout the year. There were times when tides seemed stronger, more vital, and times when they seemed to rest, to gentle themselves, as if the ocean itself needed to catch its breath. Ancient temple builders in places like India constructed massive tide gauges, stone markers that measured the exact height of high and low tides during ceremonies and festivals. These weren't just religious artifacts. They were scientific instruments. The priests recorded their measurements, compared them to lunar phases, to seasons, to the positions of celestial bodies. They were mapping the cosmos onto the behavior of water, understanding intuitively what would later be proven mathematically: that the heavens and the oceans were engaged in an eternal conversation. Indigenous peoples along the coasts of what would become North America, from the Pacific Northwest to the Atlantic shores, built their entire cultural calendars around tidal cycles. They knew exactly when certain fish would run, when shellfish beds would be accessible, when it was safe to gather food from the intertidal zones. This knowledge wasn't written in books, but was passed down through stories, songs, and ceremonies, oral traditions that encoded scientific observation within cultural memory. The tide wasn't just a physical phenomenon. It was a character in their world, as important and respected as any ancestor or spirit. That what's remarkable about all these ancient observers is that despite their different languages, cultures, and geographic locations, they all arrived at the same fundamental insight: the moon and the tides were connected. They couldn't explain how, not yet. The mechanism remained hidden, locked away in the realm of invisible forces. But they knew, through careful observation, through generations of patient record-keeping, through a willingness to see patterns and trust what those patterns revealed. They understood that the pale disk traveling across the night sky somehow reached down and moved entire oceans. This was humanity's first great insight into the tides. Not the complete answer, but the right question. Not the mechanism, but the recognition that one existed. And sometimes, in science as in life, knowing the right question is half the journey toward understanding. As we drift from ancient shores into deeper waters of scientific discovery, remember these early observers. They didn't have instruments or equations, but they had something equally valuable: attention, patience, and respect for the natural world. They watched the moon, they watched the sea, and they saw that these two things, one celestial, one terrestrial, were dancing together. They just didn't yet know what music they were dancing to. That revelation was still centuries away, but it was coming, carried on tides that never stop, guided by forces that never rest, moving toward an understanding that would transform not just our knowledge of oceans, but our comprehension of the entire universe. The moon's secret pull was about to be revealed. Imagine, for a moment, that you could see gravity, not as it affects objects on land. That's obvious enough when something falls, but as it reaches across the vast emptiness of space, stretching between worlds like invisible threads, weaving the cosmos together in a silent, powerful embrace. If you could see those threads, you would witness something breathtaking: the moon hanging in space, reaching down toward Earth with tendrils of gravitational force, and the Earth reaching back, both bodies pulling on each other in an eternal balance that keeps the moon in orbit and sets the oceans in motion. This is the hidden machinery of the tides. This is gravity's invisible hand. The story of understanding this began, as many great stories do, with someone asking a simple question: why? In the 17th century, an English mathematician named Isaac Newton looked at the accumulated knowledge of tides and lunar phases and asked why the moon would affect water at all. What was the mechanism? And in answering that question, Newton didn't just explain the tides. He revolutionized our entire understanding of how the universe works. Newton's insight was profound in its simplicity. Gravity isn't just what makes apples fall from trees. It's a universal force, Every object with mass attracts every other object with mass. The strength of that attraction depends on two things: how massive the objects are and how far apart they are. The Earth and Moon are massive, and though they're separated by roughly 240,000 miles of space, they're pulling on each other constantly. The Earth's gravity keeps the Moon from flying off into the void. The Moon's gravity pulls back on Earth, and because Earth is partially covered in liquid water, that pull creates the tides. But here's where it gets beautiful, where the science becomes almost poetic. The Moon doesn't just pull on the side of Earth facing it. Its gravity reaches through our entire planet, affecting every particle of water, rock, and air. However, because gravity weakens with distance, the water on the side of Earth closest to the Moon feels a stronger pull than the Earth's center does. And the Earth's center feels a stronger pull than the water on the far side. This difference in gravitational force, this gradient, is called the tidal force, and it's what creates the characteristic shape of tides. The water on the near side bulges toward the Moon, pulled more strongly than the rest of the planet. But simultaneously, the water on the far side also bulges outward, left behind as the Earth itself is pulled slightly more strongly than that distant water. It's as if the Moon is stretching Earth's oceans into an ellipse, creating two bulges on opposite sides of the planet. Now Earth is rotating through these bulges. As your location on Earth spins beneath one bulge, you experience high tide. About 6 hours later, you've rotated away from that bulge and you're between them, low tide. 6 hours after that, you rotate into the second bulge, high tide again, then back to low tide, and the cycle continues. This is why most coastal locations experience 2 high tides and 2 low tides every day, in a rhythm as reliable as clockwork. As predictable as the Moon's journey across the sky, the elegance of this system is humbling. The ocean, vast and seemingly chaotic, is breathing under lunar guidance. Each wave that touches the shore is part of a planetary-scale movement orchestrated by gravitational forces that bind worlds together. When you stand on a beach at high tide, the water at your feet has been pulled there by the Moon's embrace. When you return 6 hours later to find the beach expanded, the water withdrawn, you're witnessing the rotation of Earth beneath gravity's invisible architecture. But the Moon isn't working alone. The Sun, though much more massive than the Moon, is also much farther away. Its gravitational effect on Earth's tides is real but weaker, about 46% of the Moon's tidal force. Still, the Sun's contribution matters significantly. And when we consider both celestial bodies working together, the dance becomes even more intricate, even more beautiful. Think of the ocean not as a static body of water, but as a living, breathing entity responding to cosmic forces. Every particle of water in every ocean is feeling the pull of the Moon and Sun simultaneously. In the Pacific, in the Atlantic, in the Arctic and Indian Oceans, in the Mediterranean and the Baltic and the Caribbean. Everywhere water flows, gravity is orchestrating movement. The tides are planetary-scale evidence that Earth is not alone, not isolated, but intimately connected to the celestial bodies that share our corner of the cosmos. And there's something deeply soothing about understanding this. The tides aren't random. They're not chaotic or unpredictable. They're the result of fundamental forces operating according to elegant, comprehensible laws. The same gravity that creates tides also keeps planets in orbit, holds galaxies together, and shapes the structure of the universe itself. When you watch waves roll in and out, you're watching physics in its purest form. Simple rules creating complex beauty. Invisible forces made visible through their effects. This understanding transformed more than just science. It changed how humanity saw itself in the universe. We weren't living on a world separate from the heavens. The heavens were reaching down, touching us, moving our oceans, connecting Earth to the broader cosmos in ways both literal and profound. The tides became proof that we're part of something larger, something interconnected, something that operates on scales both intimate and incomprehensibly vast. But gravity's invisible hand has more to show us. Because while the Moon and Sun create the basic rhythm of tides, that rhythm plays out differently depending on how these two celestial bodies align. Sometimes they work together, amplifying each other's effects. Sometimes they work in opposition, canceling each other out. And that interplay creates a secondary rhythm, A longer cycle that adds depth and variation to the ocean's breathing. The dance of sun and moon is about to become even more beautiful. Picture the night sky during a full moon. The moon hangs luminous and complete, a perfect circle of reflected sunlight that casts shadows and turns the world silver. Now picture where the sun must be in that moment. Directly on the opposite side of Earth, below the horizon, its light traveling across space to illuminate the moon's face so perfectly. This is alignment. Earth, moon, and sun arranged in a straight line, with our planet in the middle. Now picture 2 weeks later, when the moon disappears completely, the new moon. When the moon sits between Earth and sun, its shadowed side facing us, invisible against the darkness of space. This, too, is alignment, but with the moon in the middle this time, between Earth and our star. These alignments matter. They matter profoundly, because when sun and moon align, whether on the same side of Earth or opposite sides, their gravitational forces combine. They pull together, reinforcing each other, creating tides that are higher and lower than average. We call these spring tides, though the name has nothing to do with the season. The word spring here comes from the Old English meaning to leap or to well up, a perfect description for these exceptionally high tides that seem to surge with extra energy during spring tides. High tides climb higher up the beach, reaching places usually dry. Low tides retreat farther, exposing rock formations and tidal zones typically submerged. The difference between high and low water, what scientists call the tidal range, becomes dramatic. In some places, this difference can be spectacular, with water levels changing by 30, 40, even 50 feet between high and low tide. The ocean seems more alive, more dynamic, as if responding with enthusiasm to the combined call of moon and sun. But the celestial dance doesn't stop there. 1 week after the full moon and 1 week after the new moon, the moon reaches what we call its quarter phases. From Earth, it looks like a half circle, as if someone sliced the moon down the middle. But the true significance isn't what we see, it's the geometry. During quarter moons, the sun and moon form a right angle with Earth at the corner. They're pulling at cross purposes now, their gravitational forces partially canceling each other out. This creates neap tides, from an Old English word meaning barely touching. During neap tides, the difference between high and low water becomes minimal. High tides don't climb as high. Low tides don't retreat as far. The ocean seems calmer, gentler, as if taking a rest between the more dramatic spring tides. The tidal range shrinks, sometimes by half, and coastal areas experience what feels like a pause in the usual rhythm. This cycle, from spring tide to neap tide and back to spring tide, takes about 2 weeks, following the moon's phases from new to full and back again. It's a rhythm within a rhythm, a longer beat underlying the daily pulse of high and low tides. And it means that the character of the tides is constantly changing, constantly evolving through this monthly cycle. The ocean you visit today will behave differently from the ocean you visit in a week, and differently still from the ocean 2 weeks from now. The ancient observers we met earlier noticed this. Even without understanding the mechanism, they knew that tides were stronger during full and new moons, gentler during quarter moons. They incorporated this knowledge into their fishing schedules, their travel plans, their entire relationship with the sea. The spring tides brought different opportunities and different dangers than the neap tides. A harbor accessible during neap tide might be too shallow during spring tide low water, or too turbulent during spring tide high water. Knowledge of this cycle was survival knowledge, passed down as carefully as any other vital skill. But there's yet another layer to this celestial choreography. The moon's orbit around Earth isn't a perfect circle, it's an ellipse, meaning the moon's distance from Earth varies throughout each month. When the moon is closest to Earth, a point called perigee, its gravitational effect is strongest. When it's farthest away, at apogee, its pull weakens. If a spring tide happens to coincide with perigee, the result is what some call a perigean spring tide or king tide, the highest tides possible, when the ocean seems to swell beyond its usual bounds, sometimes causing flooding in low-lying coastal areas. Similarly, the Earth's orbit around the sun is also elliptical. Earth is closest to the sun in early January and farthest in early July. This affects the sun's tidal contribution, adding yet another subtle variation to the mix. When you consider all these factors together, daily rotation, monthly lunar phases, the moon's elliptical orbit, Earth's elliptical orbit, the result is a tidal pattern of extraordinary complexity, yet one that remains completely predictable, calculable years and even centuries in advance. This predictability is one of the marvels of understanding gravity's role in tides. Modern tide tables can tell you with remarkable precision when high and low tides will occur at any coastal location, months or years into the future. This knowledge, built on Newton's insights and refined by generations of scientists, has made coastal navigation safer, fishing more productive, and our relationship with the ocean more informed. But here's what makes this dance truly profound. It's been going on for billions of years. Long before humans evolved, long before life emerged from the oceans, long before Earth even had the atmosphere we breathe today, the moon was pulling on Earth's waters, creating tides. Those ancient tides were likely much larger than today's, because the moon was closer to Earth back then, gradually spiraling outward over geological time. Some scientists believe these massive primordial tides played a crucial role in the origins of life, creating tidal pools where complex chemistry could occur, where molecules could concentrate, where the first replicating systems might have emerged. The dance of sun and moon is eternal, patient, unchanging in its fundamental nature, yet infinitely varied in its expression. It's a cosmic performance staged twice daily on every shoreline in the world, and we're fortunate enough to witness it. As the moon crosses your sky tonight, remember, it's not just reflecting sunlight. It's moving oceans. It's continuing a gravitational conversation with Earth that has shaped our planet's surface, influenced the evolution of life, and created rhythms that countless organisms, including us, have learned to live by. But the choreography doesn't end with celestial mechanics. Because once these cosmic forces generate tides in the open ocean, those tides must travel to shore. And as they do, they encounter Earth's actual geography, the shape of continents, the contours of coastlines, the depth of continental shelves. What happens next transforms the relatively modest tides of the open ocean into phenomena ranging from barely noticeable to genuinely spectacular. The secret geometry of shorelines is about to reveal itself. In the open ocean, far from land, tides are surprisingly modest. If you were floating in the middle of the Atlantic or Pacific, watching the water level around you, you'd see it rise and fall by only about 2 or 3 feet during a tidal cycle. The gravitational bulge created by the moon and sun is real, but spread across the entire ocean. It's gentle, subtle, easily missed if you weren't looking for it. But something remarkable happens when this tidal energy approaches land. As the tidal bulge, this traveling wave of elevated water, encounters continental shelves, underwater slopes, and coastline contours, it transforms. The energy that was distributed across thousands of miles of open ocean gets concentrated, amplified, sculpted by geography into forms both beautiful and extreme. Every bay, every inlet, every peninsula and harbor has its own tidal personality, shaped by its unique geometry. Consider the Bay of Fundy, nestled between New Brunswick and Nova Scotia in eastern Canada. Here, tides don't just rise and fall. They surge and retreat with almost violent energy. The tidal range in the Bay of Fundy regularly exceeds 50 feet, making it home to the highest tides in the world. Twice a day, billions of tons of water flood into this bay, creating a temporary inland sea. Then, just 6 hours later, that water retreats, leaving behind mudflats that stretch to the horizon, boats resting on the exposed seabed, and coastlines completely transformed. What makes the Bay of Fundy so extreme? The shape. The bay is roughly funnel-shaped, wide at its mouth and narrowing toward its head. As the tidal bulge enters the wide mouth, it carries immense volume of water. But as the bay narrows, that same volume gets forced into an increasingly confined space. The water has nowhere to go but up. Additionally, the bay's length and shape create a resonance effect. The natural period of water sloshing back and forth in the bay closely matches the tidal period. This creates a reinforcement, like pushing a swing at just the right moment, amplifying the tidal movement to spectacular heights. The effect is mesmerizing and slightly unsettling. Watching the tide come in at the Bay of Fundy is like watching time itself accelerate. You can see the water level rising, hear the rush and gurgle of incoming water, witness shorelines disappearing beneath advancing waves. Then the turn, that mysterious moment when the tide reaches its peak and begins its retreat. The water drains away with equal intensity, exposing a landscape that seems alien, temporary. Existing only in the brief window between tides, travel halfway around the world to the Maldives, and you'll encounter a completely different tidal personality. Here, in the Indian Ocean, tides are gentle, almost polite. The tropical atolls experience tidal ranges of only a few feet, creating calm, predictable conditions that make these islands ideal for the resorts and communities built at the very edge of the water. The reason? The Maldives are surrounded by deep ocean with relatively steep underwater topography. There's no continental shelf to amplify the tides, no funnel-shaped bays to concentrate the energy. The tidal bulge passes by with minimal modification, creating changes noticeable but never dramatic. The Mediterranean Sea presents yet another variation. This nearly enclosed sea experiences microtides, tidal ranges so small they're often overshadowed by wind and weather effects. The narrow Strait of Gibraltar restricts tidal exchange with the Atlantic Ocean, and the Mediterranean's shape doesn't favor tidal amplification. For ancient Mediterranean peoples, tides were subtle enough that other factors, currents, winds, seasonal changes, mattered more to navigation and coastal life. But then there's Mont Saint-Michel, off the coast of Normandy in France, where the tidal range can exceed 40 feet during spring tides. This medieval abbey, perched on a rocky island, becomes truly isolated during high tide, surrounded by water that surges in with remarkable speed. The phrase often associated with Mont Saint-Michel is that the tide comes in faster than a galloping horse. While that's somewhat poetic exaggeration, the tide does advance quickly here, made dramatic by the extremely flat coastal plain. As water rushes across this flat expanse, it appears to race towards shore, transforming the landscape in minutes. The science behind these variations is complex but understandable. Several factors determine how tides behave at any particular location. The width and depth of the continental shelf matters enormously. Shallow, broad shelves slow and amplify tides. The shape of bays and estuaries can concentrate tidal energy or dissipate it. The angle at which the coastline meets the tidal flow affects how much energy gets redirected or absorbed. Even underwater features like ridges and canyons channel tidal currents in specific directions, creating local variations. Some of the most powerful tidal currents in the world occur in narrow channels between islands or between an island and mainland. The Saltstraumen in Norway, for instance, is a narrow strait where tidal currents can reach speeds of 25 miles per hour, creating massive whirlpools and standing waves as billions of gallons of water rush through with each tidal cycle. These currents are so powerful and predictable that they've become both a navigation hazard and a tourist attraction, a place where the hidden energy of tides becomes visible, dramatic, even dangerous to eye in the Pacific Northwest of North America. The complex geography of islands, channels, and inlets creates a maze of tidal variations. Two locations just a few miles apart can experience significantly different tidal times and ranges. This complexity made traditional navigation incredibly challenging, but also created rich ecological diversity, as we'll soon discover. Indigenous peoples of this region developed sophisticated knowledge of these local tidal variations, understanding which channels would be passable at which times, where tidal currents would help or hinder canoe travel, and how to read the relationship between tide, geography, and opportunity. This secret geometry of shorelines reminds us that while the fundamental cause of tides is cosmic, the gravity of moon and sun, the actual experience of tides is profoundly local. The tide that touches a beach in California is driven by the same forces as the tide that surges into the Bay of Fundy. But the result is entirely different, sculpted by the specific shape of Earth at that specific location. It's as if the moon and sun are composing music, but each coastline is a different instrument, producing unique sounds from the same fundamental score, and these instruments don't play in isolation, because the tides that shape coastlines also shape life itself. Every organism living in or near the tidal zone must adapt to this rhythm. must learn to survive in a world that alternates between ocean and air, between submersion and exposure. The tide is more than a physical phenomenon. It's an evolutionary force, a selector, a creator of opportunities and challenges that have shaped biodiversity in profound ways. The creatures of the tide are waiting to share their stories. There's a zone between worlds, not quite land, not quite sea, where life exists according to rules unlike anywhere else on Earth. This is the intertidal zone, the narrow band of coastline that spends half its life underwater and half exposed to air, sun, wind, and weather. Twice a day, every day, this zone transforms. And the creatures that inhabit it have evolved remarkable adaptations to not just survive, but thrive in this rhythmic chaos. Consider the barnacle. These small, cone-shaped creatures cement themselves to rocks so firmly that trying to remove one will break the rock before breaking the barnacle's grip. When the tide is out, barnacles seal themselves inside their shells with trap doors made of overlapping plates, creating a nearly watertight chamber that preserves moisture and protects soft tissue from desiccation and predators. They can survive hours, sometimes days, in this sealed state, barely breathing, waiting, but when the tide returns, something magical happens. The barnacle opens its doors and extends feathery appendages called cirri, modified legs that sweep through the water like tiny nets, filtering plankton and organic particles. For the few hours of high tide, the barnacle feeds frantically, gathering enough nutrition to sustain itself through the next low tide period. Its entire life is orchestrated by tidal rhythm, a constant cycle of waiting, feeding, waiting again. Or take the hermit crab, that charming wanderer of tide pools who carries its home, an abandoned snail shell, on its back. Hermit crabs must solve a problem most creatures don't face. They inhabit a world where the environment completely changes twice daily. During high tide, they forage underwater, using their gills to breathe, searching for food among submerged rocks and seaweed. But as the tide recedes, they must find a tide pool, a pocket of water left behind by the retreating ocean, to survive until the sea returns. If they're caught too far from water when the tide drops, they risk desiccation and death. Watch a hermit crab navigate this challenge, and you're watching millions of years of evolution solving a unique problem. They seem to understand tide timing instinctively, beginning their return journey to deeper water or protected pools well before the water level becomes dangerous. They've internalized the rhythm, made it part of their biological programming. The moon, through its tidal influence, has written itself into the hermit crab's DNA. The ghost crab presents an even more remarkable adaptation. These pale, sand-colored crustaceans spend most of their time on dry land, living in burrows above the high tide line. But they breathe with gills, requiring moisture to extract oxygen. So ghost crabs must periodically return to the water's edge to wet their gills, making quick dashes to the surf and back. They're creatures of both land and sea, and they time these moisture-gathering trips according to tidal cycles. During extreme low tides, when the water is farthest away, ghost crabs venture farther from their burrows, taking advantage of the expanded beach to forage. During high tides, especially nighttime high tides, they hunt along the water's edge, scavenging whatever the ocean has delivered. But the influence of tides extends far beyond the visible intertidal zone. Out on coral reefs, tidal timing governs one of nature's most spectacular reproductive events, coral spawning. Many coral species are synchronous spawners, meaning all individuals of that species release their eggs and sperm at the same time. This synchronization increases the chances of successful fertilization in the vast ocean, but it requires precise timing. The trigger? A specific combination of factors including water temperature, day length, and crucially, the lunar cycle and associated tides on certain nights. Typically during spring tides following full moons, entire reefs release their gametes simultaneously. Billions of eggs and sperm float toward the surface in an underwater snowstorm, turning the water cloudy with potential life. This mass spawning, governed by tidal and lunar cues that coral polyps somehow sense and respond to, is essential for reef reproduction and genetic diversity. The moon, pulling the tides, is also orchestrating the continuation of these ancient ecosystems that lie in mangrove forests. Those remarkable intertidal ecosystems where trees grow with their roots in salt water. The tide determines everything. Mangroves have evolved extraordinary adaptations to thrive in conditions that would kill most plants: saltwater exposure, unstable muddy substrate, and twice-daily inundation. Some mangrove species use specialized roots called nematophores that stick up out of the mud like snorkels, allowing the tree to breathe even when its root system is submerged during high tide. The timing of seed dispersal, the settlement of seedlings, the flushing of nutrients, the arrival of fish seeking shelter. All these processes are choreographed by tidal rhythm. Baby fish, shrimp, and crabs by the millions use mangrove roots as nurseries during high tide, hiding from predators among the complex root structures. When the tide recedes, birds arrive to feast on the concentrated prey trapped in shallow pools. The mangrove ecosystem doesn't just experience tides, it's fundamentally structured by them, with different species occupying different tidal zones based on their tolerance for exposure and submersion. Even microscopic life responds to tides. Diatoms, single-celled algae that form golden-brown films on mudflats, have an internal biological clock synchronized to tidal cycles. They migrate vertically through mud in rhythm with the tides, moving up to the surface during low tide to photosynthesize, then retreating deeper as the tide rises, avoiding being washed away. This vertical migration follows tidal timing so precisely that scientists can predict diatom behavior. Just by knowing the tide schedule, the connection between tides and life runs deeper than adaptation to a challenging environment. Some scientists argue that tides may have been crucial to the origin of life itself. Billions of years ago, when life was just beginning, tidal pools provided unique conditions: concentration of organic molecules, cycles of wetting and drying that might have facilitated the formation of primitive membranes, protection from the harsh open ocean. The rhythmic nature of tides could have provided the environmental cycling necessary for early evolutionary processes. If this hypothesis is correct, then tidal forces didn't just shape life, they may have made life possible. Today, the intertidal zone remains one of the most productive and biodiverse ecosystems on the planet. It's a laboratory of evolution, a showcase of adaptation, a reminder that rhythms can become opportunities. The tide, which might seem like a harsh challenge, has instead driven creativity in the story of life. Every creature we've met, barnacle, hermit crab, ghost crab, coral, mangrove, diatom, carries within its biology the signature of the moon's influence. The rhythm of tides written into cellular machinery, behavioral patterns, and life cycles. And humans, watching these creatures, learning from them, have also learned to live by the tide. Our story with the ocean's rhythm is just as ancient, just as profound, and still continuing today. Stand on a dock in any coastal village at dawn, and you might witness a scene that has repeated itself for thousands of years. Fishing boats preparing to leave with the tide, not because of superstition or tradition, but because the tide determines everything. When boats can safely navigate shallow harbors, when fish will be feeding in tidal currents, when nets can be set and retrieved. The tide is not just an environmental factor for coastal peoples. It's a partner, a schedule keeper, sometimes a generous provider, and sometimes a dangerous adversary. The earliest human civilizations that emerged along coastlines quickly learned that survival meant understanding tides. The Vikings, those master mariners who crossed the Atlantic centuries before Columbus, didn't just navigate by stars, they navigated by tides. They understood tidal currents in the channels between Scandinavian fjords and islands, using these currents to assist their voyages. A Viking longship could travel much farther with much less effort by catching the right tidal flow, letting the moon's gravitational pull do work that would otherwise require human muscle and hours of rowing. In medieval Europe, the power of tides inspired engineering. Tide mills, structures that captured incoming high tides in reservoirs, then released the water through water wheels as the tide fell, provided reliable mechanical power for grinding grain. The first tide mills appeared over 1,000 years ago, a recognition that the predictable rhythm of tides represented harvestable energy. Some of these mills operated continuously for centuries, grinding flour, sawing wood, pumping water. Their turning wheels synchronized to the eternal rhythm of the moon's gravity. The Chinese developed sophisticated tide prediction techniques as early as the Han Dynasty, over 2,000 years ago. Court astronomers created tables correlating tides with lunar phases, helping to schedule military campaigns, coordinate fishing fleets, and manage transport along tidal rivers. This knowledge was considered strategic. Understanding when tides would be favorable or unfavorable could mean the difference between successful military operations and disaster. Entire naval battles were planned around tidal timing, with generals choosing to attack when tides would carry their ships advantageously, or leave enemy vessels stranded. Indigenous peoples of the Pacific Northwest developed what might be the most sophisticated, pre-scientific understanding of tides anywhere in the world. The complex geography of the region, countless islands, channels, and inlets, each with slightly different tidal timing, required deep, localized knowledge. Different Salish tribes maintained detailed oral traditions describing tidal behavior in specific locations, knowledge refined over thousands of years and considered sacred. Canoe travel routes were planned around tidal currents. Certain fishing spots were only productive during specific tidal conditions. Shellfish harvesting required knowing precisely when particular beaches would be exposed at optimal times. This indigenous knowledge represents a form of science that Western culture is only recently learning to appreciate. It wasn't written in equations, but it was observational, predictive, and incredibly accurate. Elders could forecast tides months in advance, could explain why certain locations had extreme tidal ranges while others didn't, could read subtle signs and current patterns that indicated tidal phase. When European explorers first navigated these waters, they often relied on indigenous guides whose tidal knowledge meant the difference between safe passage and shipwreck. Fast forward to the modern era, and our relationship with tides has become more sophisticated but no less dependent. Every major port in the world operates according to tide schedules. Container ships carrying billions of dollars of cargo time their arrivals and departures to coincide with high tides, when channel depths are sufficient for their massive drafts. Cruise ships, aircraft carriers, oil tankers, all the giants of maritime commerce respect the tide's authority. The digital age hasn't freed us from tidal constraints. It's simply allowed us to predict and plan around them with greater precision. But perhaps the most exciting modern development in our relationship with tides is the recognition that they represent a massive source of clean, renewable energy. The same gravitational forces that have shaped life and human civilization for billions of years can now generate electricity. Tidal power plants, particularly in locations with extreme tidal ranges, are beginning to harness this potential. The Siwa Lake Tidal Power Station in South Korea, the Rance Tidal Power Station in France, and experimental facilities in Canada, Scotland, and other countries are proving that the moon's pull can light homes and power cities. These tidal power installations work using various methods. Some, like traditional tide mills, capture water during high tide and release it through turbines during low tide. Others use underwater turbines positioned in tidal currents, functioning like underwater wind farms, their blades turning in response to the massive flows of water moving with the tide. The advantage of tidal power is its predictability. Unlike solar and wind energy, which depend on weather, tidal energy is completely foreseeable years in advance. We know exactly when tides will occur, exactly how strong they'll be, making tidal power one of the most reliable renewable energy sources imaginable. There's something beautifully circular about this development. Humans began by observing tides, learning their patterns, adapting our activities to their rhythm. We built civilizations around tidal knowledge, used tides for navigation and sustenance. Now we're returning to tides as a solution for our energy future, recognizing that the same ancient force that fed our ancestors can power our descendants. The tide that once determined when you could fish or sail now determines when you can charge your electric vehicle or light your home. Yet this return to tidal energy also carries responsibility. Because as we've learned throughout this journey, tides aren't just physical phenomena. They're the heartbeat of coastal ecosystems, the rhythm that countless species depend on for survival. Harnessing tidal energy without disrupting these ecosystems requires careful planning, environmental awareness, and humility about the complexity of systems we're intervening in, which brings us to a crucial question as we near the end of our journey. What happens to tides, to coastlines, to all the life and human civilization that depends on them? As our planet changes, the tides are ancient and stable, but they're not immune to the transformations currently underway. Climate, sea level, and the very shape of coastlines are shifting. And when they shift, the tides shift with them. For billions of years, the conversation between moon and ocean has followed the same fundamental rules. Gravity pulls, water responds. Tides rise and fall with predictable rhythm. This stability, this reliability, is part of what makes tides so remarkable. They're a constant in a changing world, a rhythm you can set your watch to, literally. But constants aren't immutable, and the tidal system we've explored is more delicate than it might appear. Sea levels are rising. This isn't speculation or distant future concern. It's measurable, observable, accelerating. As global temperatures increase, polar ice melts and ocean water expands, adding volume to the seas. Current projections suggest sea levels could rise by several feet within this century, possibly more if ice sheet collapse occurs faster than expected. This rising baseline doesn't eliminate tides, but it changes how they interact with coastlines. Imagine a high tide that currently reaches a specific point on a beach. Now add 3 feet of sea level rise to that same high tide. Suddenly, that tide is reaching areas that were previously safe, flooding neighborhoods that existed above the historical tidal zone. Storm surges, which occur when storms coincide with high tides, become catastrophically higher. Coastal flooding becomes more frequent, more severe, more destructive. The tide, which has been a predictable partner for coastal communities, begins to feel more like an encroaching threat. But the changes go deeper than simple addition of water volume. Coastal geography is changing as sea levels rise. Beaches erode, barrier islands migrate, wetlands drown. And because tidal behavior is sculpted by coastal geometry, as that geometry changes, so do local tidal patterns. Some locations might experience increased tidal ranges as underwater topography shifts. Others might see decreased ranges. Tidal currents could strengthen or weaken, following new channels carved by changing water levels. The Bay of Fundy, home to the world's highest tides, illustrates both the power and vulnerability of tidal systems. Scientists studying the bay have discovered that its extraordinary tidal range is partially due to a resonance effect that's extraordinarily sensitive to small changes. If sea level rise alters the bay's dimensions even slightly, that resonance could shift, potentially decreasing the extreme tides that define the region. A natural wonder shaped over millennia could transform within decades. Estuaries and tidal rivers face particular challenges. These transitional zones where freshwater meets saltwater, where tides push upstream against river flow, are among the most productive ecosystems on Earth. But they're also among the most vulnerable. Rising sea levels cause saltwater intrusion, the penetration of ocean saltwater farther upstream into freshwater ecosystems. This changes salinity gradients that countless species depend on, forces mangrove forests and marshes to migrate inland, if they can, if there's room, if human development hasn't blocked their path, and threatens freshwater supplies for human communities, the creatures of the tide. Those remarkable adapters we met earlier face uncertain futures. Many intertidal species are highly specialized, adapted to very specific tidal zones defined by how often they're submerged and exposed. As sea levels rise, these zones shift upward on shorelines. But in many places, seawalls, roads, and buildings block this upward migration. The intertidal zone gets squeezed, a phenomenon called coastal squeeze, trapped between rising water and immovable human infrastructure. Species that can't adapt quickly enough simply disappear. Coral reefs, those spectacular ecosystems that time their spawning to tidal and lunar cycles, are simultaneously threatened by warming oceans, acidification, pollution, and now by changes in tidal patterns. Corals are sensitive to water depth, light penetration, and current flow, all factors influenced by tides. As sea levels rise and tidal patterns potentially shift, reef ecosystems that have existed for thousands of years face conditions they've never experienced before. Yet there's resilience in these systems too, and reasons for cautious hope. Life has adapted to tides for billions of years, and that adaptive capacity hasn't disappeared. Some mangrove species, for instance, can migrate landward relatively quickly if space is available, creating new intertidal habitat as old habitat is submerged. Some tidal marshes can build vertically, accumulating sediment and organic matter to keep pace with rising water, at least up to a point. Evolution hasn't stopped, and species that can adapt quickly, those with short generation times, high genetic diversity, and flexible behavioral patterns, may find opportunities in changing conditions. Human engineering is also adapting. Some coastal communities are beginning to implement living shorelines, nature-based solutions that use restored marshes, oyster reefs, and other natural systems to absorb wave energy and adapt to changing tides, rather than rigid seawalls that prevent adaptation. There's growing recognition that fighting the tide is ultimately futile, but working with tidal systems, understanding their changing behavior, and designing human infrastructure with flexibility and respect for natural processes can help both human communities and ecosystems survive. Tidal power development, mentioned earlier, is being designed with these future changes in mind. Engineers are creating tidal turbines that can function across a range of tidal conditions, recognizing that the tides 20 years from now might behave differently than the tides today. This forward-thinking approach represents a maturation in how we interact with tidal systems, not as static resources to exploit, but as dynamic partners whose health and stability matter to our own. The fragility of tides reminds us of something essential. We live on a planet of interconnections. The moon pulls on water, gravity shapes tides, tides shape coastlines, coastlines harbor ecosystems, ecosystems support biodiversity, biodiversity includes us. Change one element, add heat, raise sea levels, alter chemistry, and effects ripple through the entire system. Tides teach us that nothing is truly separate, that the celestial and terrestrial are woven together, that what we do to oceans eventually affects everything, including the ancient rhythm that has been so constant for so long. But this isn't a story of inevitable loss. It's a story of transformation, challenge, and the possibility of thoughtful response. The tides will continue. The moon isn't going anywhere. Gravity still operates. But how those tides interact with Earth, with coastlines, with life, is partially in our hands now. We can choose to understand these systems more deeply, to protect the ecosystems that depend on tidal rhythms, to design our coastal presence with respect for forces larger than ourselves. The tide is turning, yes, but it's been turning for billions of years. What matters is whether we turn with it, adapting our relationship with the ocean to acknowledge both its power and its fragility. The same moon that has guided sailors for thousands of years is still there, still pulling, still creating tides. And we're still here, still watching, still learning what it means to live on a planet where everything is connected, where gravity reaches across space to move oceans, where the price of ignoring these connections grows steeper every day as we move toward the end of our journey, toward rest and reflection. Let's carry this understanding. The tides are ancient, but they're not unchanging. They need protection just like forests, atmosphere, and biodiversity. They're part of what makes Earth livable, beautiful, mysterious. And they're asking us, in their gentle, insistent way, to pay attention, to care, to remember that we're part of this dance between worlds. We've traveled far tonight, from ancient shores where early humans first noticed patterns in the chaos, through the mathematics of gravity that revealed the mechanism behind the mystery, across coastlines that shape tidal energy into 1,000 local variations, among creatures whose very biology is written in tidal rhythms, and finally into our own relationship with these forces, both our dependence and our responsibility. But now, as this journey draws to its close, let's return to where we began, standing at the edge of the ocean, listening to the whisper of waves, watching water advance and retreat with that patient, eternal rhythm. You understand now what moves the sea. You know about the moon's gravitational embrace, the sun's contribution, the complex interactions of celestial bodies that create a rhythm played out on every coastline in the world. You've seen how local geography sculpts these cosmic forces into unique expressions, dramatic surges in some places, gentle lapping in others. You've met the creatures whose existence depends on tidal precision, whose behaviors are choreographed by the moon. You've traced humanity's journey from tide watchers to tide harvesters, from wondering to understanding to now protecting. But perhaps the most profound realization is simpler than all that science, more fundamental than all those details. It's this: the tides are a pulse, a heartbeat, a breath. The earth, beneath the moon's gaze, is breathing. The oceans rise and fall like lungs, filling and emptying. Twice a day, every day, this breath continues, has been continuing for longer than there were beings to witness it, will continue long after we're gone. There's something deeply comforting in that permanence, that rhythm that transcends human timescales and concerns. When ancient people watched the tides without understanding their cause, they sensed this. They felt the connection to something larger, something cosmic. They were right. We're all, every living thing, every human civilization, every tide pool and coral reef and grain of sand. We're all participants in a gravitational dance that binds the universe together. The same force that keeps galaxies from flying apart is the force that moves the water at your feet. Think about that for a moment. When you're standing on a beach, when you feel the water touch your toes and then retreat, you're feeling the moon's gravity. You're experiencing a force that crosses 250,000 miles of space to reach you, an invisible hand that has been gently pulling at Earth's oceans for billions of years. There's a directness to that connection, an intimacy to it, that's rare in our relationship with cosmic forces. And the rhythm is everything. Life evolved in tidal zones, synchronized itself to that rhythm. Humans built civilizations around that rhythm. Even now, with all our technology and infrastructure, we still respect that rhythm, plan around it, adjust our activities to accommodate it. The tide doesn't care about human schedules or priorities. And there's something almost meditative about accepting that, about adjusting ourselves to this larger rhythm rather than expecting it to adjust to us. As the world becomes more complicated, more fast-paced, more demanding of our attention, the tides remain. They rise and fall at their own pace, neither hurrying nor delaying, indifferent to human urgency. You can't rush a tide. You can't negotiate with it. You can only observe it, understand it, and find your place within its rhythm. That's a kind of wisdom we sometimes forget, the wisdom of accepting rhythms larger than ourselves, of finding peace in patterns we don't control. Tonight, wherever you are, the tide is doing what it has always done. If you're near an ocean, it's rising or falling beneath the moon's pull. If you're far from any coast, it's still happening, still following the same gravitational laws, still breathing its ancient breath. You're part of that system now. You understand it, not just intellectually, but emotionally. You've walked with tide pool creatures, sailed with Viking navigators, calculated with Newton, and looked forward with climate scientists. You've seen that tides are more than water movement. They're a connection between Earth and Moon, between gravity and life, between ancient rhythms and future possibilities. Let that understanding wash over you now, gentle as waves on a quiet shore. The tide is rising somewhere, falling somewhere else, constant in its rhythm, eternal in its nature. Creatures are adjusting to its movement. Barnacles opening their doors, hermit crabs finding pools, ghost crabs timing their journeys. The moon is pulling, the earth is rotating, gravity is weaving space and time together into patterns of water and stone. And you're part of this. Connected to it through the ancient human practice of watching, wondering, and understanding. Connected through the water in your own body, which responds to the same moon that moves the seas. Connected through your place on this planet, which is itself a participant in the cosmic dance. As sleep comes, if it comes, let it come like the tide. Inevitable, natural, gentle. Let the rhythm of waves in your mind match the rhythm of tides in reality. Let the understanding you've gained become a source of peace rather than just information. The ocean is still breathing. The moon is still pulling. The ancient rhythm continues, and that rhythm will be there tomorrow, and the day after, and for countless days beyond. It's a rhythm you can return to whenever you need grounding, whenever you need to remember that you're part of something larger, something ancient, something that will continue. The hidden science of the tides isn't really hidden at all. It's written in every wave, whispered by every shore, visible to anyone who watches with patience and wonder. The tide is eternal. And in its rhythm, there is rest.